Hello, everyone, and welcome to our live session for today, the 22nd of January, 2025, our second live session of the new year. Welcome. We are happy to see you. We are happy to be here with you. My name is Matthew. I'm one of the course staff and behind the scenes folks who gets everything running here. If you are new to our live sessions, welcome. We are happy to have you here. I'll go over our quick um, kind of the way this works. Please post your questions in the chat. I will grab them from there. We see all of the questions, so please post your question only once. If we don't pick your question right away, it's because we try to go in the order that they are received, but then we also jump around to try and get a variety of topics and to give more people a chance to ask questions. We do try to keep this at a beginner level. So if you have advanced questions about quantum mechanics and topology, then this is perhaps not the right venue. But sometimes we dive um, into topics that are, complicated, and Professor Impey brings it down to a beginner level. So with that being said, thank you all for joining us. I'm going to hand this over to you, Chris. You can welcome everyone, and then I know you always have a topic for us that can spark discussion. So why don't you get started?
Right. Welcome, everyone. However you found us with the online course, or just you ran into this channel, and hopefully will subscribe. I do often start with a news story in astronomy. Today I'm going to start with something a little broader, and I'm also going to cross a little line that I normally stay away from, which is the line of politics. So I want to talk about something that may be a little strange to people outside the US, because I know we have a very international audience. And it's sort of, the question is, what's going on with DEI initiatives, diversity, equity, and inclusion? And I'll start by giving it an astronomical context. So science, for most of its history, was the domain of white men, basically, and often wealthy white men, because there was no professional science jobs, so you had to be of your own means to be able to do science. And that's gradually changed over the past century, and especially the last few decades. And in our astronomy department, we've gradually diversified our faculty. And in the level of the undergraduate program, we have equity. We have equal numbers of men and women. Graduate students, women are 35 to 40%. Faculty, maybe it's only a quarter, so it's less. But as you go up the chain, typically you see fewer women. And then when it comes to underrepresented minorities, is very few. And that's a nationwide statistic in astronomy. And it's been a very stubborn statistic to change at the level of the nation. The principle here, why should we bother, why should we do this, is that we believe, most of us who do science and educate in science believe anyone can do science, everyone should be able to do science, and everyone should have an equal opportunity to do science, regardless of what the historical landscape might have been. And so most of the people I know, most of my colleagues, are committed to, doing some level of balancing the table between the genders particularly, and then also with minorities who may not historically have done science at a high level. Well, the new administration is essentially taking a hammer to DEI, and it's doing it in two ways. It's doing it at the university level, where universities, often through state governments as well as the federal government, are essentially being forced to dismantle their diversity, equity, and inclusion initiatives completely and lay those people off, the staff who do that. This is aided and abetted by a Supreme Court decision that essentially ruled against affirmative action. And then more recently, in the last few days, with the new administration, the federal agencies are being held to this. And by the end of today, on January 22nd, all DEI employees at federal agencies will be terminated with pay initially, but then eventually they'll be relocated or fired. And so it's a dramatic change, because agencies like NSF, National Science Foundation, and NASA, who do a lot of astronomy research and fund it, have been committed to equity and inclusion and diversifying the workforce and the way they administer grants. And they've been working in that direction for decades, uninterrupted essentially. And now it's essentially going to be scrapped, if you believe the press and if you believe the executive orders. This is a dramatic change, and it's extremely unpopular in the communities I work in. There are arguments that DEI got overblown or overstepped its bounds or was running rampant. You hear various commentaries, and I'm not going to get into those. But I think very few people, very few scientists would argue that it's a bad thing to have a more diversified scientific workforce or research workforce. So we are witnessing in this country seismic change. Now, if you live in another country in Europe or elsewhere in the world, this may be a strange concept to you, and the politics of it may be confounding, and it is to many people living in this country too. But it's a big news story, and it's a story about science. It's a story about astronomy too, because astronomy is affected. So that's the topic that I wanted to lead off with today.
Excellent, thank you. Dr. Bharati kind of responds that human civilization might serve as a vehicle for preserving the diversity and beauty of life. Through technological and cultural advancements, we might protect our own species and potentially others. Okay. So I think that's, there are lots of things that can go into that. All right, we'll start with a question from Terrence, who's on with us live, who asks, good day, Professor. My question this week is about the cosmological constant. Does it, or how does it relate to the snow, quote, snow, like the static on television screens, and how is it used to complete the end of the gravity equation? How does it relate to gravity?
I'm not sure I can connect all of those things. The snow on a TV screen, and this is an old style phosphor tube TV screen, because modern digital screens with OLED detectors to give the colors don't actually have snow or static. But in an old style TV screen with a phosphor, some small fraction of the static you might see, the white noise if you like, if you weren't tuned to a station, was understood to be interactions with the microwaves of the microwave background. In other words, the relic radiation from the Big Bang. So in a strange sense, you could tune an old style TV between stations and be watching the Big Bang. Not all of that static, just a small fraction of it, but still, it's a real science experiment you could do in your home. So the microwave background radiation is, of course, the relic radiation of the Big Bang. And it only indirectly relates to the cosmological constant, which is a feature of general relativity, which was eventually realized to explain the expanding and accelerating universe that was discovered in 1995 when supernovae were observed and were used as tracers of how galaxies were moving away from us in the distant past. The accelerating expansion of the universe is explained in terms of dark energy, and dark energy in general relativity could be attributed to something called a cosmological constant. And that's a constant that means that this dark energy doesn't change with time and space. And so far as we know, dark energy does have those properties. There are interesting hints in some of the large surveys going on right now that dark energy may have varied over cosmic time. Not that it varies with direction in the sky, however. And if true, that would be a profound result, because it would be the first really important new information we've had about dark energy really for decades. And it would rewrite the story of dark energy and rule some theories out and some theories in, and really lead to new physics. So that these are interesting topics because dark energy is really under active discussion as a major component of the universe that we don't really understand at the moment.
Thank you. The next question is from Shayna, who's on with us live. Hello, Professor. What is the purpose of human civilization from the cosmic perspective, if we are insignificant but also a rare occurring phenomenon from the universe perspective?
Yes, so the role of humanity and civilization in the universe is a subject of active discussion, of course, and it's an experiment we have to do. We don't know if we're alone as an intelligent species or an intelligent or a technological civilization until we find other examples. And so SETI, the search for extraterrestrial intelligence, which is really the search for extraterrestrial technology because we don't know how to define or search for intelligence elsewhere, but we can look for technology created by sentient beings, radio technology, optical technology, and so on. So that activity's been underway for 65 or so years with no success. So we have no evidence right now that other technological civilizations like ours exist. And so logically it is possible that we're unique in that regard. And what would that mean in a vast universe where there clearly are billions of habitable planets just in our galaxy and then trillions more in other galaxies? If this is the only planet where biology not only started but developed over time to produce a technological and intelligent civilization, that would be pretty extraordinary. That would argue that we are essentially a fluke in the universe. And it's up to everyone to decide how they want to interpret that information. How would you feel if you were a fluke rather than built into the master plan of the universe? But science tends not to agree with the premise that we were built in. The idea that there's purpose in the universe in philosophy is called teleology. And it's not popular with natural scientists because natural scientists look for natural explanations in physics and other equations of science to explain what happened in the universe and how we came to be. And they don't ascribe meaning to us that way. That's sort of beyond the role of science.
The next question is from one of our live participants. Panama Red asks, how rapid is star formation in the Orion Nebula?
The Orion Nebula is a very actively forming stars right now as we speak. It's about 1,500 light years away. So when you look at the Orion Nebula, the light you see was emitted in the dark ages essentially and took 1,500 years to reach us. But the Orion Nebula, visible to the naked eye on a good dark sky, is a star-forming cloud of gas and dust where within it are young stars buried behind opaque dust, so really only directly visible if you look in the infrared. And dozens, if not hundreds, of stars are forming in the Orion Nebula right now. And we can see some of the very youngest stars in a little region of the Orion Nebula called the trapezium, which was first observed in the 1970s when we first got infrared detectors. And these stars in the trapezium are as close as we can find to protostars, so stars that are actively forming, just collapsing for the first time. So Orion, because it's fairly close by and because it's a big star-forming region, is the best object of study for us to learn how stars form.
Excellent, thank you. The next question is from Kumar Riahi, who sent an email. Last week, there was a question about whether the heliosphere protects the Earth from harmful radiation, and I was surprised by the answer, which was basically no. My understanding from previous material is that the heliosphere does protect the entire solar system from damaging interstellar cosmic radiation. Can you talk a little bit about how this functions and if it doesn't protect us, what, maybe they're thinking about the Earth's magnetic field that protects us. And so what are some of the differences between those different phenomena?
Yeah, there are two things here, so I'll keep them distinct and clear. The Earth's magnetic field does indeed protect us from solar radiation and high-energy particles from the sun because that magnetic field essentially acts as a deflector. So many of the particles, the radiation from the sun, of course, is protected mostly by our atmosphere. The high-energy particles from the sun are protected by the magnetic field because those high-energy particles are charged, electrically charged. Many of them are protons. And they are indeed deflected by magnetic fields. So the magnetic field of the Earth funnels those particles and deflects them. So Earth's magnetic field absolutely is a protective system against intense solar radiation. The heliosphere is the larger zone around the sun created by the sun's radiation, and it's not really protecting anyone from anything because it's just part of the sun's external environment. The region beyond the sun, the interstellar medium, does have radiation in it, but it's fairly diffuse radiation because the sun is essentially isolated in space. There are not stars very near the sun, and the region between stars is an almost perfect vacuum. So there's really nothing going on there. There are cosmic rays that move through interstellar and intergalactic space, but their intensity and the amount of cosmic rays is actually quite low, unless you happen to be near something like a supernova remnant, which can generate a lot of cosmic rays.
The next question, maybe you can clear up, seems to be maybe a bit of a misunderstanding. I'm not sure the premise of the question is correct, but we can discuss that. Dr. Barati asks, can we talk about the existence of aliens and then They want to know if we've ever discovered any sort of creatures or civilizations that can use teleportation or travel through teleportation.
So there is no evidence for life beyond Earth, period, as we speak in 2025, despite a lot of effort to look for signals from intelligent civilizations through the SETI program and more modest efforts by astronomers to detect life on exoplanets. We know of no life beyond Earth, of any kind, not even microbial life. So we definitely don't know of external civilizations. There's speculation that they might exist and the raw material exists to form life, and there's plenty of time for that life to evolve and get sophisticated. But at the moment, there is essentially no evidence, so it's not really a scientific subject at this point. The idea of civilizations that might be involved in teleportation, something that we are not able to do, is again in the realm of pure speculation. It's fun to speculate, but essentially that's a science fiction concept because physics does not easily allow for teleportation. You can have quantum entanglement, which will create entangled, coherent quantum states, even across large distances. And so at a very modest level of individual atoms, you could imagine something like teleportation of the transmittal instantaneously of information about individual atoms. But teleportation of a physical object, which would involve trillions and trillions and trillions of atoms, is absolutely beyond the pale in terms of our technology. So while you could speculate that eventually we might be able to do it or some other civilization might be able to do it, it's essentially the realm of science fiction.
The next question is from Herdianch, who asks, Sir, how can something be older than the universe itself? I read about a star named the Methuselah star, or Methuselah, that is estimated to be 14 billion years old, where the universe is only 13.6 billion years old.
So it's correct. The universe cannot hold anything that's older than itself because the universe is everything. I'll correct those numbers. The universe age is about 13.8 billion years, not 13.6 with the latest data. And the Methuselah star has an age, but it's an estimate. So the important thing here is that the age of the universe, measured through microwave background and distant galaxies, has an error attached. I mean, there's an uncertainty to that 13.8 billion, maybe a 5 or 8% uncertainty. But the age of individual stars is a much more difficult thing to estimate. So while the best estimate of a Methuselah star age might be 14 billion years, the error on that is likely to be 10 or 20%. And 20% of 14 is, of course, several billion years, and that easily accommodates the age of the universe. So until a star age is measured very accurately and is found to be older than the age of the universe, there is no conflict and there's no problem.
The next question is from Tamal Sarkar, who's on with us live, who would like to know, what are wormholes?
Wormholes are hypothetical constructs from general relativity where there is a rupture in space-time and one region of space-time interconnects to another physically remote region of space-time. So it requires a high degree of space-time curvature for that kind of rupture or connection through space-time, a portal if you like, in space-time to occur. And while it's allowed theoretically and in principle, there's zero evidence that wormholes exist in the universe we live in. It's hard to look for them also, but everywhere we look, except for black holes and dense neutron stars, space-time is essentially flat on the largest scales. So we see no evidence that space-time is convoluted or interconnected or tessellated or like a Swiss cheese of the kind you might expect if there were wormholes. So I think at the moment they just sit as a possibility, a hypothetical construct of general relativity.
The next question is from Adrian Murray, who's on with us live. Is the catalog of subatomic particles that we understand limited because the rest are simply beyond our reasoning abilities?
Well, the standard model of particle physics has been a successful agenda of high-energy physics for half a century. Since the discovery of quarks, the postulation of quarks in the 1960s and then their demonstration in the 70s and 80s, we have a suite of subatomic particles, fundamental particles that includes quarks, electrons, muons, and other more evanescent particles that decay rapidly. This landscape of subatomic particles is called the standard model of particle physics. And the last piece in this standard model was put in place when the Higgs boson was detected in 2013 and 2014. There are other subatomic particles that exist, but almost all of those have very short lifetimes. They can be created by accelerators and in labs, but they disappear almost immediately, turning into radiation or decaying into other fundamental particles. So there is indeed a particle zoo that includes dozens and dozens and dozens of particles, but the fundamental stable particles is a very modest number, and that number hasn't changed for decades.
The next question is again from one of our live participants. Vic Desh asks, hi, Professor, what do you think about the current plans for Mars exploration and colonization?
It depends on whose plans you're talking about. NASA has a plan for Mars colonization and exploration, and that's on a very slow trajectory because NASA is committed through the Artemis mission to going back to the moon first within the next few years. The problem there is that they're depending in part on the Space Launch System, which is proven to be very expensive and tricky to get going. They're also using Elon Musk's Starship for this now, so they're collaborating with SpaceX. And that's to the moon. The Mars for NASA is well off into the future. NASA's having trouble getting the funding for the Mars sample return, which is not colonizing at all. That's just using robots to stage samples that a robot lander eventually brings back to the Earth. And that has ballooned in cost to over $10 billion, and the timeline of that is stretched to more than a decade from now. So if you follow that timeline, then Mars colonization through NASA is decades away, 2, 3, 4 decades. We don't even know, and there's no money for that in their budget. Elon Musk, of course, is talking aggressively about going to Mars, and that's what the Starship really was built for, his best rocket, which has undergone, I think, its 7th test flight in the last week or so, where the capture of the chopsticks maneuver was successful for a second time, but the main rocket exploded catastrophically. And now the FAA is investigating, and Elon Musk's Starship has actually been grounded for a while. So Musk's timeline for Mars colonization is always seen as fanciful, basically, when he talks about it, because he talks about being there by the end of this decade. I think by the end of next decade it is possible if Starship pans out and is very successful. And then there are other private enterprises, and the Europeans are interested in Mars exploration. But nobody has a plan for Mars colonization that could come to fruition within less than 20 years, in my opinion.
The next question is from Dave W., who's on with us live and asks, can you please describe the measurement problem in physics?
The measurement problem in physics is foundational to quantum mechanics and quantum theory. And the measurement problem basically revolves around the fact that at a subatomic scale, the act of measurement changes the thing you're measuring. So there's no such thing as sort of independent measurement or the dispassionate observer or the sort of observer or experimenter who doesn't interfere with their experiment. The act of observing changes the outcome. That's a foundational issue of quantum theory. It's not a problem in a sense, it's just built into the theory that at the level of small particles, the act of observation will change the situation you're trying to observe, and therefore the outcome you get will depend on how you observed it. So it's called a measurement problem, but it's not necessarily a problem, it's just a feature. It's not necessarily even a bug of the quantum theory, it's just how the theory works. And people who want to understand the physical universe just have to work within the limitations of the fact that when you measure something, you alter it.
The next question is from Hernan Reyes, who says, I've been reading your book, Encountering Life in the Universe. In chapter 7, the author discusses some of the ethical, societal concerns. And my question is, does the Outer Space Treaty still require that space exploration take all measures necessary to avoid harmful contamination of any planets or moons we explore? And is this treaty still active, and is that one of the stipulations?
So the short answer is no. The Outer Space Treaty is really not helpful or doesn't really say anything about contamination, the contamination issue. The Outer Space Treaty of 1965, one of only 2 UN treaties dealing with space, at its core, it bans the testing and use of nuclear weapons in space. A very important thing to have done, and that treaty was signed eventually by almost every country in the world and in the United Nations. But it's really mute to the idea of ownership in space or responsibility for taking care of space. The UN does have a working group. It's a continuous working group that meets every year in New York at the United Nations headquarters and works through a series of topics. And they are charged with protecting space and dealing with the contamination issue. And they've made resolutions and made protocols and working agreements amongst their members and drafted language that might eventually become part of a treaty, but there's been no new space treaty since the Moon Treaty of 1979. So these agreements that they come to are completely voluntary. So there are agreements out of this working group that talk about protection of space, but they are voluntary, and so people don't actually have to adhere to them.
The next question is from Thelia Smith, who's on with us live. What information or finding from the James Webb Space Telescope has been the most fascinating to you?
Well, I think the discovery with James Webb of very mature, fully formed large galaxies with massive central black holes, maybe 1 billion solar masses, in the first 500 million years of the universe is a very exciting discovery, because it says that the activity of building galaxies and growing black holes happened not only very early in the universe, but very quickly. And that's a challenge to theories. It doesn't rule out theories. It doesn't say we have no idea how galaxies form or black holes form, but it's definitely challenging because simulations and simple theoretical expectations held that it would take about 1 billion years to grow a big galaxy and a big black hole. And we're seeing that it can happen in maybe 300 million years. That doesn't sound like a big difference, but it is a big difference, because it gives you very little time to build something from small pieces or a smooth gas that's that size. So that, to me, is the most exciting result so far from James Webb.
The next question is from Lawrence K. There are a few kind of related issues in here, so I might just break them up. The first one is dark energy constant throughout the universe?
Possibly. We would expect dark energy to be constant throughout the universe if it obeys the rule of the cosmological constant as formulated by Einstein. And as the term implies, it is a constant, so the energy density of dark energy in a region of space does not change over time or with location in space. And that was the case through most observations, but in the last year or two, some surveys that are designed to diagnose dark energy have hinted that it might not be constant. But I would just say the jury is out on those measurements. They're very difficult, and this is not a firm enough result that people are claiming it's the case yet.
So then the related or follow-up question is as you kind of indicated, does the expansion rate of the universe vary either through space or through throughout time?
Yes, the expansion rate of the universe absolutely varies over time. It doesn't vary in direction, however. The universe is isotropic in the sense that if every direction you look out in space, you see more or less the same thing. You see more or less the same galaxies, you measure the same range of redshifts, and you see the same expansion behavior, either through historical, by looking back in time. But as far as the expansion rate over time, it of course has changed, because the universe started small and has grown through expansion, and the expansion rate has changed. It was originally decelerating for some period of time, 7 or 8 billion years, and then in the last 4 or 5 billion years, due to the growing dominance of dark energy, which has a constant strength, while dark matter is sort of being diluted by its expansion through bigger volumes of space, dark energy has taken over, and that's led to an accelerating expansion. So the expansion rate of the universe is varied continuously since the Big Bang.
The next question is from Time with Chocolate, who's on with us live, who asks, what exactly is a gravistar? Is it a real object? Is it theoretical?
It's a theoretical object that has a very intense gravity in the center. It's a massive star, which could have strange forms of matter in the interior. People always also talk about quark stars, where the density and the pressure are such that you could actually liberate quarks, which are normally contained within subatomic particles like protons and neutrons. But a gravistar is more or less a theoretical concept than an observed phenomenon.
The next question is from Jim Rittenberg, who asks, is it true that only like 1 to 5 new stars form per year in the entire Milky Way galaxy?
That's right. The star formation rate in the Milky Way overall is a modest number of a couple. 1 to 5 is about the right range. Maybe we know it a little more accurately now. And that sounds like a very low number because the Milky Way is a big object with hundreds of billions of stars. But of course, the Milky Way is also a very old object. And so, in a million years, which is a small fraction of the age of the galaxy, that's 3 or 5 million new stars forming. So a few stars per year doesn't sound like much, but a year is a tiny fraction of the age of the universe and the tiny fraction of the evolution time and age of a galaxy. So, in the aggregate, when you integrate over time, that is a lot of stars being formed.
The next question is from Karem, who's from Turkey, and asks, if we consider the current astronomical trends, what fields will astronomers focus on in the future? And what do you think are the most promising areas or fields of research?
Well, two of the fields that are very prominent and hot right now will continue to be hot in the future in the next 10 or 20 years. It's fairly safe to predict that cosmology will continue to be a hot field because we're still learning about the universe and we don't know what dark matter and dark energy are. And just to figure that out will be a future project of cosmology for it to succeed, really. And exoplanets is the other area because we've been able to discover many exoplanets. The census of confirmed exoplanets is something around 6,000, but that projects to an enormous number in the galaxy. In the next decade or so, we're going to see the characterization of those exoplanets and hopefully and possibly the detection of microbial life off Earth. So those are the hottest two subjects in astronomy right now, and they are fairly safe bets to be the hottest subjects for a decade to come.
The next question is from Timothy DeWeese, who asks, sent an email asking, I would like to know which are the best resources online for keeping up with the latest exoplanet discoveries and research.
Well, NASA is the best resource there because NASA funds a lot of the exoplanet research. They funded not just individual researchers, but they funded space missions, of course. They funded the Kepler satellite that discovered most of the exoplanets that are out there now in a 5-year mission. It was incredibly successful. And NASA runs a couple of websites, one of which is the Exoplanet Catalog, and another one is a website that has more detailed information about the exoplanets, about characterizing them and their parent stars and the properties of those stars, and any follow-up observations we've had of them. So NASA is the best source for keeping up with exoplanets, and those websites are maintained and kept very current.
The next question is from Terrence, who asks, Professor, do neutron stars, can you talk a little bit about neutron stars and their characteristics? Is the surface ionized, and do they have starquakes?
So a neutron star is a stellar remnant. It's the corpse of a star that started life as maybe 8 to 10 times the mass of the sun, went through its life very rapidly because massive stars have short lives, created nuclear fuels, ejected some of its envelope in the late unstable stages of stellar evolution, and then when the core collapsed, if the core was between 1.5 to about 3 or 3.5 times the mass of the sun, then it is compressed by gravity to a state where reverse beta decay occurs. Protons and electrons merge to form neutrons, And then you have pure neutron material, because the neutrons have no electric charge. They can sit right next to each other. And so a neutron star is essentially a huge atomic nucleus with neutrons sitting right next to each other, touching. That's what a neutron star is. It's a dark object because it's not got fusion going on. It's just a big particle ball. And it does have starquakes because the star that formed it was rotating, and the neutron star in its collapses by orders of magnitude, and so the spin rate goes up by orders of magnitude. So it's exceptionally rapidly spinning. We've seen millisecond pulsars, because a pulsar is a neutron star that has a hot spot that emits radio waves. So we have neutron stars that we know are spinning hundreds of times a second. And the stresses induced on the neutron material by that rapid rotation do indeed lead to the neutrons rearranging themselves, and the rupturing, and starquakes can be the result. And we've measured those starquakes. People who monitor the pulses, especially of pulsars, which are the neutron stars we can observe with radio telescopes, have seen the pulse rate change in a way that indicates starquakes occur. So this is an observable phenomenon.
The next question is from Wendy Traver, who sent an email. Do you think that the fact that in quantum mechanics, quantum realms, particles pop in and out of existence lends any credence to the multiverse theory, where universes might also pop in and out of existence?
So that's a big stretch to connect those two things, but I'll comment on them for sure. It's a good question. Antiparticle pair creation is a phenomenon of physics that's been known for over half a century, and it's seen in the lab. So it's uncontroversial that out of pure energy you can form particle-antiparticle pairs, which will then annihilate very quickly and go back into radiation. The spontaneous creation of a particle-antiparticle pair is fairly different from the spontaneous creation of a universe. There are mechanisms that are thought to be plausible for what might happen in the very first iota of time after the Big Bang, when space-time was highly curved and interconnected, where you possibly could have little bubble universes emerging, and that would be a mechanism for a multiverse. But that theory is not very well developed. It's based on physics we don't simply understand, because we don't have physics that can talk about the Big Bang that early. So the multiverse idea, whatever faint echoes it might have with particle-antiparticle pair creation, is in a much less firm category as a scientific idea.
The next question is from Keith and Trish Crum, who are on with us live, who asks, there are 6 planets visible in the night sky currently, 4 with unaided vision. Can you talk a little bit about what this alignment or this, this arrangement is, how it comes about, and how often it happens?
So having this many planets in the sky is very unusual, and it doesn't happen very often. In fact, the last time anything like this happens, the word that gets used for this is syzygy. That's a sort of global planetary alignment, with the planets all being in one particular small part of the sky. It is unusual because if you think about it, the planets' orbits are very long, and they're all on different orbits, so they're at different places relative to the sun through their orbits compared to each other. And the outer planets have orbits that are decades, so you can sort of see intuitively that when you have outer planets that have orbital times of a century or so, the odds of 2 of them lining up, they're moving at different speeds in their orbits, of course, so the odds of them lining up are very low. And you really only expect to see a full alignment like a syzygy every few centuries. So actually it is really unusual, and it's also unusual because we had one only half a century ago.
The next question is from Elaine, who sent an email. Hi, I recently visited the Kitt Peak Observatory 2 weeks ago, and I was quite interested in the DESI project. Can you talk a little bit about that, specifically the objectives of it, and when we can expect the first results to be published?
Yes, DESI is the Dark Energy Survey Instrument, and it was a very clever way to take a venerable telescope, the Kitt Peak 4-meter telescope. 4-meter telescope is not large by modern standards. It's a middle-sized telescope. When it was built in the early 1960s, it was one of the biggest in the world. So this telescope is an old venerable telescope and has been rejuvenated with an extraordinary camera behind it, which takes exquisite pictures of large areas of the sky and different filters. And this telescope has been repurposed from being a general purpose telescope with different instruments and different observing projects to really spend a lot of its time doing one thing with this special camera. And that one thing is to survey the sky with exquisite accuracy and multiple filters. And that's the dark energy survey. And what it's looking for is imprints of dark energy, for instance, through weak gravitational lensing and the way different environments of galaxies evolve over time. And it's been very successful. It's taken a lot of data. I think it's in its 5th year. And it's been releasing the data year by year. So the data is being published and has been published for several years now. The main results of the survey will require almost all of its data to be in hand because it's a very challenging task that it's been set. So these intermediate results and releases of data year by year are not telling us anything dramatic yet, but I think we're close to the time when they'll pull all of that data together and maybe we'll learn something very exciting about dark energy.
The next question is from Hurdianch, who's on with us live, and asks, I heard that Michio Kaku built a particle accelerator in his mom's garage. How are particle accelerators built, and is it possible to make them with things around you?
Well, I've not heard that story. It wouldn't surprise me. Michio Kaku is a very well-known writer and science communicator, and he's more theoretically inclined, so I'm interested to hear that he was experimenting with particle accelerators even as a child. If you want to build a modest particle accelerator like a cyclotron, yes, you can do it in your garage, and you can do it with modest amounts of components. The first particle accelerators, which were cyclotrons, were built in the 1930s and 40s at the Lawrence Berkeley lab, and Lawrence was the physicist who did that and won a Nobel Prize for it as well. And you know, a modest particle accelerator, you need a strong magnetic field, you need a way to inject electrons and see them spiral in the magnetic field and get accelerated, and you need to create a vacuum within that instrument. Those things are all possible with fairly modest technology. I'm not saying it's dime store purchases, but you know, a few $100s could get you in the ballpark if you're willing to do some of the machining yourself. So yes, it is possible to build a modest and historically accurate accelerator in your garage with fairly modest investment of time and money.
The next question is from P51. There's sort of two related questions in here, so I'll divide those up. P51 asks, what is the Hubble constant as the first one?
Hubble constant is the current expansion rate of the universe, named after Edwin Hubble, of course. It isn't a constant over time because the Hubble constant is the current expansion rate of the universe, and the expansion rate has been changing over time. At the current expansion rate is measured in the local universe by looking at nearby galaxies and how they're moving and their distances. And the local Hubble constant is measured to be about 70 kilometers per second per megaparsec. And that means that as you go a megaparsec, or 3.3 million light years away from the Milky Way, a galaxy will typically be receding or moving away from us at 70 kilometers per second. And if you go twice that far, it will be moving away from us at 140 kilometers per second, and 3 times it will be 210 kilometers per second. So it's a scaling that tells you the recession velocity of a galaxy at a particular distance, and that itself is telling you the expansion rate.
The second part of the question is, could it be that the main bubbles, I'm not sure if they mean of like expanded space or expanding space or of matter in them, but is it possible that something in the surrounding space around our galaxy could fade out or shorten or enlarge distances the way we see different distances, like when you're looking through water?
Not sure I know the sense of the question. I mean, you're going to have to repeat that. That didn't make total sense to me.
Okay. Basically, is there a way that, so as you look through water and you see Like, look at an angle through water and you see, like, if you look like at a straw, you'd see it in a different position, or you'd see something distorted. Is there something around our galaxy that could possibly be distorting, distances or arrangements of galaxies?
So in part, this is a question about whether we live in a particular special part of the universe. And the answer generally is no. There's nothing strange about our part of the universe. The Milky Way and Andromeda and a few dozen dwarf galaxies live in what's called the local group. And the region beyond that is a pretty good vacuum. It's intergalactic space with big voids. There's nothing particular that happens in those voids. Those voids don't focus energy or create refraction or distortion the way the analogy in the question was being framed. So there's no sense that our region of space, the sort of vacuum of space beyond the Milky Way, is strange in any way or distorts our view of the more distant universe.
The next question is a second question sent by Hernan Reyes, who is asking about the international decision-making processes related to space tourism and commercialization. Basically, are there any rules for things like terraforming planets at a planetary scale? Are there any rules governing those kinds of things? Or is that stuff that is coming in the future that still needs to be done?
The simple answer is there's no international space governance at that level. The United Nations is the logical body that would develop rules about terraforming, about major activities in space or mining asteroids or things like that. And while they have a working group that discusses issues that include that, that has not led to any new treaties or any binding language on nations. And it's also not even been pursued very aggressively by that body. So they were interested in space debris, for example, particularly. So the answer is no, there's no governance. And so individual countries or individual entrepreneurs, oligarchs, businessmen, tech titans, whatever you want to call them, are free to follow their own whims as regulated by their government. And the US government has a very hands-off approach. It's a highly deregulated environment for space launches, for space activity, a very light hand on the rudder, and so there's very little ruled out, and there's certainly no government proviso against terraforming a planet or the moon or Mars or anywhere like that. So, and I don't think any other countries have rules either.
The next question is from Arif Roni, who asks, the European Space Agency's excuse me, Milky Way mapping Gaia mission has completed its sky scanning phase. Can you talk a little bit about what that mission is and what are its goals and what are your opinions of it?
Gaia was a very successful mission, a European camera that was observing the sky and mapping the positions of stars extremely accurately. And the big picture view of Gaia is that it was mapping the positions and motions of close to 1 billion stars. It's an enormous number. It's a small fraction of the stars in the Milky Way, so that's still only looking, if not in our backyard, in our immediate neighborhood in the Milky Way galaxy. But it's an enormous number, and so it's giving us incredibly detailed information on the galactic environment of the sun and the way the Milky Way rotates, where the nearest spiral arms are and how they are behaving. And also because of the technology used to measure these positions, this Gaia mission was very sensitive to exoplanets and was able to find dozens, and probably in the end hundreds of exoplanets. So it is one of the more successful missions in the past few decades.
The next question is from one of our live participants. Is the Higgs boson a field or a particle? Can you talk a little bit about what it actually is?
It can be thought of either way, and the word boson refers to a particle because there are other particles in the standard model of particle physics, the W and the Z, two different types, so there's 3 W and Z particles that are also bosons. The word boson is a reference to an Indian mathematician, Bose, referring to integer spin particles. So that's all that boson really means. It could be any integer spin particle. Higgs boson is more correctly thought of as a field rather than a particle, because although it was detected as a resonance at about 130 giga-electron volts in the CERN collider, in the Large Hadron Collider, what it does is it operates as a field permeating space. The properties of that field attribute mass to particles. The Higgs mechanism is a mechanism whereby this field generates mass for particles in space or moving through the field. You think of it as a viscosity, where a more massive particle has higher viscosity and moves slower in the field, and a lower mass particle has less viscosity and moves faster in the field. So it's more correctly thought of as a field than a particle.
The next question is from Pakornin, who asks, why are there no green stars?
There are no green stars, because green is a monochrome color as part of the spectrum. Red, orange, green, blue, indigo, violet. It's in the middle part of the visible spectrum. And so while green has a wavelength that corresponds to the middle of the visual range, stars have a wide range of energy production. And so a star is never a monochromatic emitting object. It never emits a single narrow sliver of wavelengths, which would make it look green, say, or yellow, or red. The star emits energy across a wide range of wavelengths, and the average wavelength of its emission might actually be at a color we would call green, but because there's a lot of shorter and longer wavelengths, there's blue and red light mixed in there, what you end up in the end is sort of a white or yellowish star.
Excellent, thank you. The next question is from one of our live participants. What would a neutron star look like?
A neutron star would be very hard to observe. In fact, the naked neutron star is essentially unobservable because it's a dark, very small object. It's an object the size of a few kilometers across, and the nearest examples of these neutron stars are hundreds of light years away. So you're trying to look at something that is completely dark because it emits no energy, and it's extremely small and it's extremely far away, is almost impossible to detect. So we cannot detect neutron stars directly. The subset of neutron stars that we detect and have in catalogs is the few thousand where there's a radio hotspot and they're detected by a radio telescope as pulsars. So we are cataloging and detecting pulsars as the sort of subset of a much larger population of neutron stars that have radio emission.
The next question is from Nashon Darrow, who asks, why has it been rare for bodies to hit the Earth where there are human settlements? Is it about probability and the relative size of the Earth in the cosmos?
Yes, I think the impacts occur on the Earth, and they're quite rare. We believe that a sort of Tunguska-like event, Tunguska was it was a bolide that exploded above the Earth's surface and then flattened 10,000 square kilometers of forest in Siberia and apparently killed nobody because it was so low populated area in 1908. That kind of an event should occur about once every 100 years. So that's pretty rare already. And most of the Earth, although most of the population of the Earth, 70 or 80%, live in cities, those cities occupy a tiny fraction of the Earth's surface. Really, so the odds of an impact hitting a heavily populated area are luckily quite low, and an impact that could cause damage and kill people is also quite rare, only happens every few hundred years basically. So that is good news for us because it means this is not something we should generally worry about.
The next question, excuse me, is from one of our live participants. Can you talk a little bit about the space debris in outer space? How dangerous is it for astronauts? And is it possible to clear space garbage from orbit?
Space debris is a huge problem, and it's recognized to be a huge problem. It's just getting worse. As we throw up tens of thousands of satellites into low Earth orbit, many of them will deorbit naturally, but we're gradually accumulating debris. When these things bump into each other and hit each other, they turn into shrapnel. They release many more smaller particles, each of which can cause damage. So the International Space Station, which is in a high low Earth orbit, 350 miles up, It's pretty much been the case for a decade, and certainly the last 5 or 6 years, that the astronauts every year, sometimes multiple times a year, have to shelter in place where there's a potential impact with the space station of a piece of tracked space debris that would cause a catastrophic failure, a rupturing of the skin of the space station, and possible damage or to the station and death to the astronauts involved in the worst case. Sheltering in place means the astronauts go away from the arms of the space station into the central hub where there's more mass to shelter and protect them, and they may even use internal airlocks to seal themselves off from the arms until the debris has passed or moved away. So that happens routinely, so it's clearly a risk, and that risk seems to be increasing, and the number of shelter-in-place incidents with the ISS seems to be increasing year by year. As for doing something about it, that's a very big problem. Space agencies around the world are thinking of mitigation strategies, but space is big and the debris is spread out over a large area, so no one's found an efficient way to get rid of it.
The next question is from an email. Ananya asks, my question is that if the sun disappeared, I understand that the light, the sun is 8 light minutes away from Earth, and we wouldn't see, the light would disappear and it would go dark. But why is it that the Earth would lose the gravitational influence of the sun? Why is the gravitational force the same, and why is it not instantaneous?
Well, if the sun reached the end of its life, it wouldn't disappear in that sense. So the sun's light could disappear when the fusion finishes in the sun and it moves to a later stage of evolution. But the sun still exists as a physical object, and its gravity is dictated by its mass. So unless the sun loses a lot of mass suddenly, and the sun will not lose all its mass explosively, it will not die as a supernova, then the gravity exerts on the Earth will not change. So you can have the sun going out, or the light from the sun being extinguished because fusion is over, while the sun still exerts the same gravity.
Excellent, thank you. The next question is from one of our live participants. Let's see here. Sorry. Can you talk a little bit about why, can you talk about the Big Bang? Why did it happen? What was around before the Big Bang? And what was the history of that?
I mean, these are unfortunately questions cosmology and astronomy and science in general can't answer. The Big Bang is a physical description of the universe as it evolves from an early, hot, dense, small state. But the Big Bang idea, concept, or theory, whatever you want to call it, does not include a cause. It does not specify a cause, and does not specify what happened before. So just being very pragmatic about what the Big Bang theory does and doesn't do, it unfortunately doesn't answer the two questions.
Excellent. Thank you very much. It's now 11 o'clock. I think we will take one final question before we wrap up, and then that will be the end of it for today. So thank you to everyone for joining us. The final question for today is, why is it so expensive to get space missions into space and to travel between planets?
Space exploration is expensive because of gravity, essentially. Fighting the Earth's gravity is a very difficult thing. And so you have to build a rocket, and you have to fuel that rocket. And historically, the Apollo missions, for example, with the Saturn V rocket, that you were using 75% of the mass of that rocket to accelerate the little spacecraft, 4%, to the moon. So it's very inefficient because you're using, almost the entire mass just to burn fuel to get the object going fast enough to leave the Earth's gravity. So that's the real reason it's expensive. It's also because we're using chemical fuel, which is a very inefficient form of fuel. It means you need a lot of it. And so most of the time with a rocket, you're just accelerating the fuel itself, which you have to carry. rather than the payload itself. And so that is, in a nutshell, why space travel is expensive, because you have to burn a very inefficient source of energy. You have to spend most of that energy just launching the fuel itself rather than the thing you want to get into space. And that creates a large mass and a large expense. And also the technology of creating a rocket engine that has to operate at very high temperatures and with very high pressures and stresses, that's expensive to develop. So building rocket engines is not trivial. It costs a lot of money, takes a long time, and all of that means space travel and space exploration is unfortunately quite expensive. Good questions this week, as always, varying across a lot of subject matter, so thanks. And we have the next 3 live sessions all mapped out, I think. Matthew can say when they are, and I hope you join us in the future.
Excellent. Yes, thank you everyone for joining us. The next live sessions will be on Thursdays. We're going to be doing Thursdays for a while, probably for this semester, because of other meetings that have come up and taken over Wednesday time slots. So the next session will be in 2 weeks on Thursday, February 6th. So that'll be the next one. And then if you would like to hear about future live sessions, make sure you like this video and subscribe to our channel and click the little bell icon so that you hear about upcoming live streams. And then also, if you'd like to, you can scroll back up to the top of the chat, and I posted the link for a Google group. And if you'd like to join our Google group, then we send out announcements for those every week before the live sessions begin. So thank you all very much to everyone who joined us today, and we look forward to seeing you again in 2 weeks. Take care.